Hello and welcome. In this presentation, which is topic 9, we're going to provide further discussions on the design of generalized functional observers. In particular, we're going to look at an even more general functional for the following time delay systems. So this generalized functional has multiple time delays in there. And of course, when we have FDD equal to 0, it comes back to the previous discussion. The reason why we include this is to show the generality of estimating this problem. Also, in our chapter 6, where we look at the estimation of the delay unknown input, we also have a special case where we're going to estimate a generalized functional where C matrix here is 0, and we have CD, which is non-zero, and we have F here 0. So the reason for estimating this even more general functional is a valid reason for doing it. And this one is from chapter 16 in our book. So we go straight into chapter 16. That's where we provide further discussions on the generalized functional observers for this generalized functional. And it's mentioned in here that the results will be used or are used for the estimation of unknown inputs, where the situation we have is the output measurement vector is actually being delayed. So we come to that chapter 6 later on, but at the moment we just like to consider the estimation of this generalized functional for the following time delay system. Okay. So what we do in here is we propose a very general structure for this functional. And this observer structure has multiple internal delays. As you can see in here, it's contain an internal delay and also another internal delay, which basically multiple internal delays. And we also can have the output measurement vector delay up to 3 times. This is to cater for the situation where the generalized functional contains up to 2 time delays in here. And so when we propose this observer structure, to ensure the existent conditions, we follow exactly the same approach as in our previous discussions. So what we have in here, we have a number of unknown parameters. We require to find them such that the estimation, which is this thing here, converts to asymptotically to the true functional. Okay, so we follow an exactly same process, and so we can omit the detailed discussions here. What we do, we present the existing conditions. So what we say in here is that we can ensure that the generalized functional converts asymptotically to its true functional, the estimation, provided that this time delay system is asymptotically stable. You can see that now we are actually looking at an error time delay system with multiple delays. And so that where, if you can look at chapter 20 in our book, where we discuss about the stabilization problem or the stability of problem based on a well-known existing results in the literature. So that one is required to be asymptotically stable or exponentially stable. And then the rest of the parameters of the observer, like J, JD, JDD, and all of that, they can actually be obtained from the parameters of the observers, like M, MD. What important in here is the 1, 2, 3, 4, 5 couple matrix equations. Now we have actually up to 5 couple matrix equations. Out of these matrix equations, we need to solve for matrix N, ND, NDD, T tilde, W hat, U hat, and Y hat. And so these are all defined in our book. So what we basically want to do here is to provide the necessary and sufficient condition for the existence of the solution of these 5 couple matrix equations. And so the processes follow exactly the same as what we discussed previously. And that's tell us that the unified framework that we took in this book, we basically can work for a wide range of time delay systems. The approach is we define an error vector and we systematically taking the derivative of the error vector, and then we arrive at these existing conditions. So when we look at it, we can say we can stack all the unknown input matrices into one big matrix, and we call it X tau. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we arrive at the if and only if condition, and when we have a look at this big matrix here, all those matrices, like for example, F, FD, FDD, they all present in this big matrix here, as well as the matrix CD as well. And C tau is just this combination of C and CD. And also this matrix is basically is known because of or we know all the generalized functional matrices F, FD, FDD, and matrices A and AD. They are part of the time delay system itself. So this is the well-known if and only if condition in terms of the rank of the matrices. And then once the condition is satisfied, just like before, we obtain solutions in the term of the generalized arbitrary matrix. And then we can express the solution of the error of the time delay system in terms of that free arbitrary matrix. If it is non-zero, I mean, if these submatrices N2 and N_D2 and so on, they're non-zero, then we have this general time delay error time delay system. And so it's just a matter of stability analysis or stabilization, where we find this arbitrary matrix to ensure exponential stability. And this is basically discussed in our chapter 20. So that basically the highlight, the outline of the approach that we took in here in dealing with the problem of estimating this generalized function for this class of time delay system. So we can cater for all different scenarios, like C can be 0 as well. And that is an interesting bit that we're going to explore further on in the numerical examples. So let's have a look at the examples where we're going to show um, the generality of our results. Okay. And so what we do is we're going to take a numerical example, and this example is taken from a reference. We see reference 24, which is a paper where we did a while ago. And that in this particular paper, we show the relax in the existing condition compared to reference 2 in here, where we propose a more general structure observer. And so we take an example from there. And in this particular example, we have matrices A, ID are given here, and matrix B, C. CD is 0. That is where in those references 24 and 2 did not discuss the situation where CD is non-zero. And also the functional that needs to be estimated is only the stack variable x3. So it's just a functional observer where the t is basically consists of the stack variable x3 of t. Now, so that's a specific situation as a special case discussed in this topic. Okay, so that's basically what the functional is. It's just the stack variable x3 that we like to estimate. And so in the reference to the author, there proposed an observer which has an internal delay in there. And this observer, we basically discussed this in the previous topic. In order to obtain the system conditions for the observer parameters, this is the necessary requirement for it. It's the necessary and sufficient condition for the system of the observer parameters, but it does not guarantee that the result is a stable observer. So anyhow, this is the observer required there. And what demonstrated in this example, in this reference, is that when it comes to the requirement to estimate this stack variable, this existent condition is not satisfied. So what it implies is this observer structure here to estimate this stack variable does not exist. Does not exist. So and what is saying that if we are looking for a first order observer of this structure to estimate this variable, stack variable, for this time delay system, it does not exist. And so in the reference, so before we go into the comparison there, we can also say that, look, the conditions given in here is a special case of our general condition, which is 1620. 1620 is basically this big matrix here. It's catered for all those structures, so extra FD, FDD, and NDD, and all of that. And what we're telling here is, look, if we let all of these submatrices to be 0. So in other words, we don't have stack delay in the output measurement. We don't estimate the generalized functional. We don't add in extra term in the observer structure and stuff like that. So if they are zero, our existence conditions according to the phi metric equations, which are given in here. These phi couple metric equations, they boil down to two couple metric equations. That's what they are, and they are given in here. Okay. And so if we have these two couple metric equations, we can stack them together, and then we can realize the necessary and sufficient conditions for the existence of these unknown matrices to satisfy these two couple metric equation, and they turn out to be this condition. Okay. And then so we know that this condition does not exist, so the observer structure of this form does not exist. And then come along the authors in this reference propose a more general observer. And what's specific about this structure and by these by the authors proposed in this reference is that there is an extra term MD in here, and as well as there is an extra term in here and also there. So what this one telling us is it's a very logical way of thinking. Basically, if we want to relax existence conditions, we need to impose a more complex structure to provide, exploit, generate more information, extract more out of that. And that is in the term of this extra delay output measurement. So this is the observer structure proposed by this reference. And they show that with this modification, we have extra terms. The existence condition is turned out to be this existence condition. And so when we check this condition for this numerical example, we can then find that the condition is satisfied. Okay. So this condition is satisfied, and that's why it's a relaxation of the earlier reference 2 there. And then we can carry on to design a first order observer, which basically of this structure here. Okay, and what we like to show in here is, okay, if we look at this structure, then we can actually obtain the existence condition exactly the one given as in here. And this is basically letting CD equal to 0 because the authors in reference 24 did not consider the case where CD is non-zero. So that was for the case CD equal to 0, FD and FDD equal to 0. But they did not discuss the case where NDD is non-zero. So we got all of these terms, all the metrics, we let them equal to 0, and then our 5 metric equations, they boil down to these 3 metric equations, couple metric equations. And then with these 3 couple metric equations, if we stack them into an augmented form, we can also derive the necessary and sufficient condition for the solvability, which is basically this condition. Okay. So what we are saying here is our general approach to addressing the general functionals. They cater for all the previous results. That's what we're saying here. Now, we want to go one more step further. We want to show the generality of observer, the one that has this non-zero metric NDD in there. So because in our observer structure, we actually propose an extra, we add in an extra term in our observer structure, which is that NDD omega t minus 2000 there. We also have that extra term and so on. What we are going to show is, look, how about we consider another example? How about we consider another numerical example? And in this numerical example, we're going to select different matrices I and ID. All right. So we say, look, let us try to design a functional observer to just estimate the unmeasurable stack variable x3 of t. Now, remember in this example in here, we have only one output measurement, which is x1 t. And when we want to estimate x3, stack variable x3 of t. So we're going to do the same, but we change the matrices I and ID to the new ones as given in here. Now, if we have this kind of time delay system, what happening is that when we go into design a first order functional observer, and when we test conditions 624 and 629, 624, 1624 is from this reference, which is this observer structure. And 629 is this condition, which is from this reference. So it has a more general structure than this structure. We find that none of them actually satisfy. We found that neither of the conditions. So what that means is first order observer, according to reference 2 or reference 24, they do not exist. Of course, another point here is if we increase the order according to like augmentation approach, we can design a second order observer. But that's not the point of the discussion in here. What we're saying here is if we test the first order observers based on conditions 24 and 29, they do not exist. Now, what we can do is we can then say, okay, how about we use our observer structure. When we use our observer structure, we need to deduce conditions for the specific case where this matrix is 0, and because we only addressing a linear system with no stack delay in the output measurement vector, and also it's just a standard functional. So FD and FDD are 0, and we again we have the 5 conditions, the 5 matrix equation. They boil down to 4 matrix equations, and then what happened? We have this FDD equal to 0. The reason for that is, let's have a look at FJDD. JDD is 0. This is because CD and FDD is 0. Okay, so we don't have to have that matrix in the observer structure for this specific case. So the story is we get 4 matrix equations, and then so we stack them together, and then we obtain the following existing condition. This is for the solvability, the if and only if condition for the solvability of these 4 couple matrix equations. Okay. And so we got this like an extra row block in here compared to the reference 24. That's basically that. But the good thing is when we actually apply this condition and we check it, it's actually is found to be satisfied. So what does it mean? It means that by employing a more general structure, which contains um, multiple internal delays, we can actually relax existing condition found in the literature. Okay. And so we continue on with the design of a first order observer with multiple internal delays. And we found the following observer parameters. Okay, we found the following observer. We obtain a time delay system, which is basically a stable time delay system. Okay, a stable time delay system. We can also show the codings in here. And in this particular example coding, we got matrix I, ID, and all of that. And then when we test reference 2 in there, we find that the condition does not satisfy. The reason for that is because the rank of matrix OD is 6, whereas the rank of the matrix where we augmented the extra row in there, which is UD, is actually does not exist. And likewise, when we test the other condition, is also not satisfied. Okay, they're not satisfied. So when we check the rank of UN, it's 7, whereas the rank of ON, which is 8. And so we then apply our condition, and it turned out to be satisfied. And then we can obtain the rest of the observer parameters. When we look for the rest of the observer parameters, we have matrix N, matrix ND, and matrix NDD. So we obtain a time delay system where we did not consider the stabilization because we didn't get any extra degree of freedom in the generalized solution, in the solution of the metric, the big augmented metric equation. The reason for that is because this metric UHH, which is the one UHH here, this one has the size of 8 by 8, 8 by 9, sorry. So its rank is actually full. It's a full row rank matrix. So when we solve for the solution, we didn't get any extra freedom in there. And therefore, the error time delay system consists of only the fixed matrix N and D and NDD. It turned out that the good thing about this is this error time delay system is stable. Okay. So that means that we can actually ensure the error converts to 0 asymptotically. And when we did the analysis using the LMI condition in our reference, we found that it's actually stable with this beta value. So what we said here, even though the first order observer by the form, which is the seamless form, similar form, then which is in reference to, even though that observer structure is similar, it does not exist. The observer in here is even similar than our observer. It also does not exist. We can still design a first order observer, which is the one given in here. The price that we pay for it is we need a few more extra delay terms. You see, we need a few more extra delay terms. And those extra delay terms, they are the one associated with this delay, internal delay, omega t minus 2 here. That 2 stands for 2 taus there. And also we got an extra term in here. Okay, well, that is the trade-off. That is what the price that we had to pay for. If we go for a first order observer, other works, they don't exist. Those observers don't exist. We had to pay a bit of extra for it. And the condition that we have in here, we can see that clearly. This condition is less conservative than the condition provided in this reference. This condition here less conservative than this condition, and that's what demonstrated by a numerical example here. But then we say, look, we can even have a less conservative condition than this one as well. And that is the result of employing a more general structure observer, okay, in this discussion in here, which is the one given here. And when we look at what we have in here, we can see that our results also cater for all different scenarios. And that's what we're going to do next in the next few numerical examples. Okay. By the way, in the book, in this chapter, we also discussed that if we want to design a second order observer, we can do it. That's not a problem. In fact, a reference 2 and reference 24 can also be applied to obtain a second order observer. Of course, seeing reference 2, we can find it. That gives us a similar structure than reference 24. So that's we can employ reference 2 to design a second order observer. And that's done by an augmentation approach. So we insert one more row, and so instead of estimating one variable, we estimate two unmeasurable stack variables. And so that this is the simulation of our result using our first order general structure, where we have an extra internal delay in there. So what I like to show here is I cut and paste the simulation results. It might take a little bit of time to do it. So this is where we estimate X3 and X3 hat. Let it run there, and then we go back to here. Now we can also design a second order observer, which give us observer with just one internal delay in there. It gives us fewer delay units, but more proportional gains and more integrator and so on. But however, it gives us better error convergence because we can actually ensure that the beta conversion is actually faster, bigger. Okay. So the next example that we want to show is to run it. The next example that we're going to do is we demonstrate the design of generalized functional to estimate this generalized functional, where we got delay in the stack vector and two delays in the stack vector as well. So, and the output contains the intended stack variable and also the delay stack variables, which is given in here. And so this is like a very general functional. Okay. And so we can actually follow the same process where we say, okay, let's go for an observer first order, and then we test the condition. When we test the condition, and it's found not satisfied, so that first order does not exist. And then so again, what we're going to do, we're going to uh, this is the simulation result for it. Okay. So we then say we increase the order. And when we increase the order, and that's where we can exploit the freedom in selecting the row in here. Now, in here, we just pick the row, and for this example, just pick one in there. We found that the rank is full, and then we can then say, all right, if this condition is stable, I mean, if the condition exists and if it results in a stable observer, then that's where we can say we got a second order observer. So we test the condition and we found it satisfied. And then we are a bit greedy here. We say, look, why don't we test it where we want it without internal delays, whether it exists or not. And that's where we make all the block rows associated with ND and NDD, they all zero. We see this modified matrix in here. And so in the situation where we want to make it entirely without internal delays, we found that the condition does not exist. And so what are we going to do next? What we're going to do next is say, okay, we can either pick one internal delay. And the reason why we pick the first internal delay is because if we make this one zero, that means the error time delay system there has the smallest time delay in there, which is only tau, and that's the reason behind that. So we go for the situation, we can just say, let's pick ND, and let's make NDD equal to zero. So this is like the reference of the structure of the observer. The case where NDD is zero means that ND is non-zero. So we're dealing with the stability of a time delay system, which a smaller time delay. That's exactly what it is. And then we test this condition. We test this condition. And when we test this condition and we found that it's actually satisfied, and then so we went ahead and we solved the stabilization problem. And then we arrive at a second order observer with an internal delay. And this is the structure of the observer. So for this example here, when we want to estimate the generalized functional, which is this one, for this system, what happens is we can actually employ a second order observer. We can employ a second order observer with an internal delay, and we can ensure that the error time delay system is stable, where we did actually solve the stabilization of the error time delay system, and we arrive at this observer structure. Okay. So this is the case where it is with an internal delay. And the simulation also show that we can estimate the stack variable asymptotically. Okay. Now, what we want to do next in here, and by the way, we also have the codings for these examples as well. And so we can cut and paste them, and then we let it run, and we can have a look at the the simulation result once it is done. So we're estimating the first one and its estimation. We see the stack variable that we wanted to estimate. Okay. Now, to make the problem more interesting, we can also show that, look, let's deal with that example 2 again. Let's relook at it again. And what we want to do is we want to estimate the entire stack vector. Now, have a look at the parameters of the example. We have, remember, the information about the output measurement here. We can't get any of the stack variable explicitly. So in here, what we want to do, we say, okay, for this problem, let's us estimate the 2 stack variables for this time delay system. Okay, let us estimate the 2 stack variables. And let us employ an observer without internal delays. And so we want to estimate this functional. So which basically the entire stack vector because F is identity. So can we do that? That's the question. Now, when we actually just test the condition, when we first test the condition, where we pick these matrices associated with the generalized functional because they are 0. That's where we wanted to estimate this vector in here. Okay, not satisfied. So what it tells you is for that problem, if we want to estimate the 2 stack variables using an observer without internal delays, second order observer without internal delays, it does not exist. And the problem there is because F here is already a full rank matrix, okay? Just like we discussed before. If we don't employ any extra freedom in these matrices, and if we keep increasing more extra row in there, it doesn't work. And this is where the issue is. Without looking at this generalized functional, and if our objective is to design an observer with our internal delays to estimate these variables, standard problem using this functional observer to estimate this function does not work. So we have to stop there. Now, in our discussion, because we can cater for a whole heap of generalized functionals, we can actually proceed further. We can actually say, okay, no problem. Let us design a third order observer. Design a third order observer. Let us design a third order observer. And when we design a third order observer, we then say, okay, let's add in an extra functional for it. And this extra functional observer for it is basically, we just basically, and that's the simulation results. Okay. We just add in a delay stack variable. So we estimate x1, x2, and x1 t minus tau. And with this extra term in here, we can actually test condition again. And it's found that it is satisfied. And when it is satisfied, we can actually go ahead and check the stability of the desired observer. And the metric n itself is actually stable. Okay, it's actually stable. It's now independent of time delay, and it's stable. So that allows us to achieve a third order observer. Okay, a third order observer. This third order observer allows us to estimate these stack variables x1, x2 of this system, Now, this system, we have a look at that. It has dimension 2. It has two variables, x1 and x2. But to be able to estimate those two stack variables, and to employ an observer without internal delays, we can actually do that. Okay, so that's the significant about it. We can actually do that. And the observer that we have is a third order observer, And that third order observer estimate the two unmeasurable stack variables as well as this extra delay there. That extra delay is variables there give us extra degree of freedom. Okay, and so that also possible. That's also possible. And so let's have a look at simulation results. We also have something simulated result here. This is the third order observer from there. And so we only need to insert extra functional, and that's extra functional itself is really the delay stack variable x1. Okay. And so that shows the generality of our design approach. We will just wait for the simulation result to come up. This is just basically telling us that yes, we can actually design a third order observer for it. Now, the other significance that we want to show in here is we can even consider the case where this matrix C is zero. Matrix C is zero. So what does it mean? Let's have a look at example 3. Because matrix C is zero. So if matrix C is zero, what does it mean when we have a look at example 3, which is example 2 in here? When matrix C is zero, we have in a situation like the output measurement vector does not have any instantaneous stack variables in there. So let's have a look at the system description itself. When we look at the system description itself, when we have the situation like C equal to 0, what it's one telling us is the output measurement vector here is in fact containing a delay version of a combination of the stack vector. So we can think of like we have a situation like at the output measurement there, it's sent over a long distance, and that information is being delayed by tau. And so the output measurement that we receive is a delay version of the stack vector, delay version of the combination of the stack vector. This is a very intriguing situation, very intriguing situation. So the information, the output measurement vector that we receive is a linear combination of the delay stack vector. Okay, so that's where the simulation is delay stack vector. So we're using delay information of the stack variables in our output measurement, and we reconstruct the stack instantaneously, the stack vector instantaneously, and that's what this example 4 is telling us. All right. So this example said that that let's look at the situation where c equal to 0. And let us reconsider example 3, which is basically C0, and we want to estimate this entire stack vector. All right, entire stack vector. So we want to estimate this entire stack vector, which is basically the instantaneous information of the stack vector using the delayed output measure. That's what it is. You see that? So we consider the problem of estimating the stack vector, where the output vector contains only delay variables. Wow. And that leads us to another very intriguing situation problem that we should investigate in the future. This leads to the idea like we can use this observer structure like to compensate for the effect of time delay. And that is something later on we can look into it later on. And what we want to do in here, we can even say, look, to make it more interesting, we want to design observer to estimate this stack vector using this delay output measurement. And we want an observer with no internal delays, And that would make it even better because it can the stability of the time delay error system can be stable independent of delay. Okay, what we are telling here is, look, we follow the same approach. In other words, we just test the conditions, the condition given in here. We just test this condition. Now, because matrix C is 0, have a look at that, C is 0. So it turned out that the condition still satisfied, okay? When we test it for this problem, even C is 0, the overall rank of this condition here still satisfies. So we look into it, we zoom into this one, we see that there's a very specific structure for the metric n that is the result of the solution of this metric. And this is something that the reader can further look into this problem. So we basically telling that fi and fi multiplied by metric I, this is like they belong to the space there, and so on. So we got a metric n times fi is equal to fi times I, and so we have a specific solution for the metric n in there, okay? But when we go and look at this problem and we apply the same process, we obtain this solution in here. And it actually tells us that, look, we can even, where is example 4? We can even obtain the stable third order observer without internal delays. Have a look at this bit here. That was what I'm referring to. You see that metric I actually appears in here, because for numerical example 2, we got metric I in this bit here. So it turned out this bit here is a stable matrix. Okay, so this is something I like to remark here. To be able to realize a stable observer, we can see that the metric n here has a submetric associated with metric I in there. And what happened in here, even though we got delay output measurement, the observer that we design can ensure that we can instantaneously estimate the two unmeasurable stack variables. That's what the outcome of this is. And when we think about it, this is something unheard of because we got the output measurement. We see the delay output measurement. It contains only delay stack variables in here. So the output measurement for this example, when we got c equal to 0, the output is basically a combination of x1 t minus tau plus x2 t minus tau. We use that output measurement vector and we reconstruct an observer. And the observer that we obtain is this one in here. It's actually enable us to asymptotically estimate the unmeasurable stack variables. And that's the significance of the problem that we're considering here. Okay, so let's quickly go and have a look at the simulation results. So in here, what we're having is the situation where we got matrix A is given and ID is given, and here matrix C is 0. There, you see that. And matrix CD is the one. So the output measurement is a combination of x1 t minus tau and x2 t minus tau. And this is the two variables that we want to estimate, and we insert an extra row, which is basically only that bit in there. And so we cut and paste this, and then we obtain the solution for the matrices. And then we get the matrix N. The eigen of matrix N is stable. And so we got a stable observer. And let's have a look at the rest of the simulation. So what we have in here, we implement that third order observer without internal delays. And then we run the simulation to show the estimation of the variable x1 and its estimates. And we can also look at x2 and its estimates as well. And what we are seeing here is that with our results, we can actually instantaneously estimate, okay, figure 16.6. So this is the estimation of the unmeasurable instantaneous x1 and x1 hat. Okay. And similarly, this is the one. This is for the case where c equal to 0. Now, I let this one run a little bit, but I like to show the significance of this. I like to explain the significance further. When we look at this example, the system itself is stable, but we can even consider a case where the time delay system itself is an unstable time delay system. So like in here, when we check the eigenspectrum of this time delay system, it's actually a stable time delay system. And so people might then say, okay, if its time delay system is stable, well, it's the observer is a bit not very general, yeah, because if it's stable, it's basically die out to 0 and all of that stuff. So whatever happen in here, we can actually modify. We can actually modify the system itself. And we did a further analysis into that, and then we say, look, we can even consider the case where we change the parameters in matrix ID, and as a result, the time delay system itself becomes an unstable system. You see, this is the estimation of the delay using the delay output measurement. Okay, and this is the instantaneous estimation of it. Now, we can actually do the instantaneous estimation using delay output measurement for unstable time delay system. How about that? That's what we are doing here. and we can get a third order observer without internal delays, and we can ensure stability of it. Okay. So this one, because the system unstable, so we don't restrict the range of it. It will blow up to infinity, but the tracking is still asymptotically tracked that. And so what we see in here is we required when we look at the metric n for the case where c equal to 0, when we look at it, we see that the metric itself, the metric n itself contain this submetric n in there. Okay. And so it's important that metric n should be stable, but we do not impose the requirement that the time delay system is a stable time delay system. How about that? So that means that we can actually estimate instantaneously the stack variables where we use delay output measurement. And the time delay system itself does not need to be stable. And that's what we are doing in the next simulation in here. In this next simulation, we actually look at the situation where we have an unstable time delay system. So we change the parameters in here. The system I in here is stable, but a stable I matrix doesn't mean that the time delay system is stable, because time delay system stability depends on the metric I and ID. So we pick in this example an unstable time delay system, and we want to estimate the two stack variable instantaneously using the delay output measurement. And that's what the simulation is actually happening at the moment. It's still running. Okay, so when it's finished, we can show you the simulation. And so after that, we then also look at another example. In this chapter, we look at another sample where we consider the situation where C is 0 and CD is something and F is 0. And this particular example is given so that we can then use it to estimate the delay unknown input in chapter 6. All right. So, and then we can basically say no problem at all, whatever given to us, C, F, and so on. We can test our condition, and then if it's satisfied, we can then proceed with the design. And if we can get a stable observer, whatever there, and that's where our design is complete. Okay. So in conclusion, in this now have a look at that. So we also achieve asymptotic estimation for an unstable time delay system. For an unstable time delay system. When we look at the simulation in here, you can see that the observer, the estimation, and the one that instantaneously they actually convert to each other for an unstable system. So you can see that the significant or the intriguing, the interesting outcome based on the estimation of a generalized functional. Okay. And of course, it requires further investigation. And we are basically telling that, look, there is a possibility for us to look at a new research topic where the observer that we have, like for this particular observer, this observer itself can also be considered as a delay compensator. A delay compensator. So we could have a situation where the system itself the matrix C is 0. And so the output measurement itself, we can think of it, it's just like we collect the output measurement and then it's sent over, and therefore it's been delayed by a certain time. And then if that certain time is smaller than the delay here, we can make it the same, and therefore the question there is the output measurement is delayed. And so how can we use that output measurement vector to asymptotically estimate the instantaneous stack vector of a time delay system? We show in example 4 in this chapter that it is possible. This is possible. Of course, there is a constraint requirement that the metric n there, the sub n there is basically is a by the eigenvalues of that is a subset of the eigenvalue of metric n, metric I, sorry. And so there's a requirement that metric I should be stable if we want to estimate the entire stack vector instantaneously. Now, a metric I is stable doesn't mean that the time delay system is stable. So we can still cater in for the situation where the time delay system is an unstable system, and that's what we further discuss in this numerical example. We pick an unstable time delay system. We use the delay output measurement. We can still estimate instantaneously the stack variables, unmeasurable stack variables. Okay, so that is something the reader can further investigate. And so in conclusion, what we done in this chapter, in this presentation, is to show that, look, we actually look at a general structure observer to estimate a more general functional. Okay. And we also demonstrate that with this extra term in there, even for just a standard functional observer problem, we have relaxed the existing conditions from the previous references, like 2 and 24. And so we will, in the next presentation, we go back to chapter 6. We go back to chapter 6 to look at how do we estimate an unknown input of a time delay system where the output measurement vector is not instantaneously. So that came from whatever we just discussed in example 4 here, yeah. And then also example 5 is used for the reconstruction of an unknown input where the output measurement vector is delayed, it's not instantaneous. And so the question there, can we estimate an unknown input for a time delay system with delay output measurement? The answer is yes. However, we can only estimate delay unknown input. Okay, and that's what we discuss in the next chapter. Which is in the next presentation, chapter 6 in the book. Okay, so thank you very much for watching, and I hope I see you again in the next presentation. Bye for now.